In this video, we're going to look at some common chemical reactions. So there are some chemical names of types of reaction that you should have come across before, which include combustion, precipitation, neutralization, redox, and displacement, which is a type of redox, and also decomposition. And alongside this, in your organic chemistry, you should have come across addition, substitution, and condensation. But because these are covered in a lot more detail in organic chemistry, I'm not going to go over those in this module. So let's look at combustion reactions first. Can refer to substances such as metals. So we should know, for example, that magnesium reacts with oxygen, gives off large amounts of heat and light energy. And generally that's what combustion is, the reaction with oxygen, giving off heat and light. But generally, we're going to be looking more at combustion in terms of the reaction of a fuel, which contains hydrogen and carbon. And this means that when the hydrogen and carbon containing fuel reacts with oxygen, it makes carbon dioxide and water. So this makes the balancing of combustion equations relatively straightforward, so long as we follow a simple rule, and that is to balance the oxygen last. Let's have a look at some examples. So C11H22, and we know that it's going to react with O2 to make CO2 and H2O. So all we have to do to balance it, looking at the right hand side first to do the oxygen last, is that we're going to need 11 CO2s, and we need that because there are 11 single carbon atoms, and so each carbon dioxide contains 1, so that's 11. And then there are 22 hydrogen atoms in my fuel. Water contains 2 for each molecule, so I'll also need 11 H2Os. Doing a little bit of adding up now, I can see that on the right hand side, the products, in terms of oxygen, in my CO2 I've got 22 oxygen atoms, 11 times 2. In my water I've got 11 times 1. Adding that together, that gives me 33. Well, that's awkward because it's an odd number. Doesn't matter. Two options here. I can either double everything up and write 33 lots of O2, or I can simply write 33 over 2, or I can work it out, whatever that ends up being, 16.5 O2 molecules. So you are allowed to have halves in front of diatomic elements, so things that have even numbers, Cl2, O2, H2, etc. Second possible equation, we've got C4H10 plus O2. Working out what that's going to give me, it's going to be 4 carbon dioxides and 5 waters, and again I'm going to have an odd number, so I'm deliberately choosing some more challenging examples here. I've got 8 plus 5, 13 oxygens, 13 over 2, so I can write that as either 13 over 2, 6.5, or 6.5, however you want to express it, it's fine. Last one is an alcohol, ethanol. I'm still going to follow the same idea, so 2 carbons makes 2 carbon dioxides. Now I've got to be careful with my hydrogens because the formula is structural, so I've got to group them together. There are 6 hydrogens, which means there are 3 H2Os. Once again, just because I'm hammering this point home, we've got an odd number of oxygens because we've got 4 in my CO2, 3 in my water, that makes 7, 3.5 oxygen molecules are needed. The next type of reaction we're going to recap is precipitation. So we're going to explain what's happening with a few diagrams, and we're going to say we're going to start with 2 ionic solids. So if I write the formula AgNO3, that's my silver nitrate, NaCl is sodium chloride, and if I have S in brackets to represent solid, this is what I'm talking about in 3D, a lattice arrangement of oppositely charged ions all attracted to each other with ionic bonds. That's what we mean when we say it's a solid. But both of these solids happen to be soluble because all nitrates compounds are soluble and all group 1 compounds. So if I take some silver nitrate, and add it to water, we then have AgNO3 brackets AQ, aqueous. That means all the ions have separated out from each other. They're surrounded by water molecules. And the same thing will happen to NaCl when I put sodium chloride in water, because of course that's soluble too. And both of these solutions will be clear, so I'll be able to see through them. There'll be no light being scattered, because light is scattered by solid lattices and not by ions in solution. Doesn't mean they won't have a colour. For example, if I put copper sulfate in water, it will be blue, but it will still be clear and see-through. In this case, neither of these two compounds happen to be coloured. And we can write the ions separately. So actually when we write AgNO3, what we really mean is that the Ag+, the silver ion, is on its own in solution surrounded by water, and so are the nitrate ions. And in my sodium chloride beaker, those are separate ions too. In a precipitation reaction, what we start with is those two beakers, the aqueous solutions of soluble solids. So I have got two solutions, I mix them together, and it happens that silver chloride is an insoluble solid. So when those red silver ions from the left-hand beaker start to come into contact with the orange chloride ions from the sodium chloride beaker, then they will form stronger ionic bonds which will actually stop the water molecules from surrounding them, and they'll go back to forming a lattice. So if we look at where the chemical change is that's happening, the silver ions and the chloride ions are changing. So over here we've got silver plus, which is aqueous. We've got a chloride with a minus, which is aqueous. Remember, when we write it as a solid, what we mean is this is a change that's happened. Ionic bonds are formed between the silver and the chloride ions. But meanwhile, the nitrate ion over here hasn't changed. It's in solution, the green ones, still in solution, no chemical change, it still has the state symbol AQ, and the same for the sodium ions, which are over in the other beaker. They've stayed surrounded by water molecules. We call those ions that haven't changed, the sodium and the nitrate, the spectator ions. I would still see the same precipitate if, for example, I had a solution of potassium chloride instead of sodium chloride, because the sodium ion doesn't make a difference to the reaction. This means that I can write an ionic equation for precipitation. I can simply write that the Ag+ reacts with the Cl-, both of them in aqueous state, to make AgCl in solid state. This is an ionic equation. We're going to have a whole video about ionic equations, so I won't say any more about that for now. We're also going to look at neutralization. Neutralization involves the reaction of acids, and there are a few common acids that you should be aware of. Hydrochloric acid HCl, nitric acid HNO3, sulfuric acid H2SO4, and ethanoic acid is our first example of a weak acid, which will do a lot more when you do a little bit more organic chemistry. So there aren't actually many examples of acids, and the top three are really the strong acids, the ones that we use the most unless we're doing organic chemistry. And then with our bases, you've got metal oxides and metal hydroxides, metal carbonates. So when they come together, they're going to create particular combinations of products. One thing that's going to be made is a salt, and so hydrochloric acid is going to make a metal chloride salt, nitric acid will make a metal nitrate, and sulfuric acid will make a metal sulfate. Ethanoic acid will make a metal ethanoate. And then the other products totally depend on the base. So the name of the salt depends on the acid, chloride, nitrate, sulfate. The name of the other product, or the formula of the other product, depends on the base. All of those bases contain oxygen. In the reaction, hydrogen from the acid reacts with oxygen from the base to make water. All three examples, oxides, hydroxides and carbonates, will make water. And then the carbonate will also make carbon dioxide. And this is actually clearer when you look at the symbol equations. So we're going to look at how you balance symbol equations, because like combustion, we can use some simple rules to balance symbol equations for neutralization. So the main thing that is happening in any neutralization reaction is that the hydrogen from the acid is reacting with the oxygen in the base, or the anion in the base. And in this case, the negative ion or anion is OH minus. So it just so happens that when I put together H plus and OH minus, I make water. I don't need any balancing in this reaction. And so those two are coming together, H plus and OH minus, to make water. And if I balance my hydrogen in a neutralization reaction, it generally follows that the rest of the equation will also work. Here's another example. This time the negative ion in the base is oxide, so that's O2 minus. Now I can't just put one H plus with O2 minus, that will make me OH minus, I won't have water. So I'm going to need two H pluses, which means because HCl only has one H plus, I'll need two HCl's. Now that I've done that, can you see the whole of the rest of the equation is balanced? I have CaCl2, I have two Cl's for my HCl, I have two H's and an O to make H2O. Everything is sorted. H2SO4 plus Na2O. Again, I'm going to use the idea of how many hydrogens do I need? What do I need to do? Well, again, I've got oxide, which is 2 minus. This time though, my acid already has two H pluses. It's H2SO4. So actually, this is already balanced because my two H's go with my O to make H2O, and then my Na2 just goes in front of my SO4. Slightly more difficult example, but not too bad. Calcium carbonate and nitric acid. So the carbonate ion has the formula CO3 2 minus. And we're making more than just water this time, we're also making CO2. So the carbonate ion can be thought of as basically if we lose CO2, which is over here, then the thing that's left over, I've got one oxygen atom because it's CO3 with a 2 minus charge because CO2 doesn't have a charge. So if I take CO2 away from CO3 2 minus, I'm left with an O2 minus, which is the same balancing as reaction with an oxide. And so if I have just the one O, because the other two are going in CO2, I will need two H plus ions. They come from the acid. I will therefore need two HNO3s because there's only one H plus in nitric acid. Now you can see the nitrates are balanced too, because there are two NO3s over here and two NO3s in calcium carbonate. So neutralization reactions should not be hard to balance. If you're having difficulty, it's because you've probably got a wrong formula somewhere. For example, if I try to write CaCl as my formula for calcium chloride, which we can often do when we get a bit lazy and don't think about it, or if I try to write NaSO4 instead of Na2, then it's going to be impossible to balance. We can also represent neutralization by ionic equations, but we're going to look at that in the next video. Finally, we're going to have a quick look at redox. There is a separate video on this, so I'm just going to concentrate on how we can easily tell whether a reaction is redox or not. So our basic explanation from right at the start of GCSE is that oxidation involves a gain of oxygen and reduction is a loss of oxygen. So we can say in this reaction that magnesium becomes oxidized. However, that's quite limited. You will also see occasionally that hydrogen is like the opposite element to oxygen in the way that it bonds. So oxidation can be called a loss of hydrogen and reduction can be called a gain of hydrogen. You'll see that a little bit more definitely in organic chemistry later on. But really what we probably want to concentrate is this idea about loss and gain of electrons. So that's all very easy to remember. Oil rig oxidation is loss of electrons, reduction is gain. But how can we tell just by looking at an equation whether electrons are lost or gained if we don't have a half equation? So here's some example redox equations. The main thing to remember is that metals and non-metals form ions when they form compounds. Ion formation involves loss or gain of electrons. So in any reaction, if you see an element that becomes a compound on the other side, sodium turning to sodium chloride, that is a redox reaction. Alternatively, you could see an element that is in a compound on one side and then becomes an element. So in that first example, Na has no charge. On the other side, it becomes Na plus. So it had to lose electrons to do that, and the chlorine is gaining. There is redox happening. In the second one, that's a displacement reaction. The magnesium starts as an element, no charge, loses electrons, become a 2 plus. It must be doing some redox, and the copper vice versa. In the second displacement reaction of chlorine and sodium bromide, chlorine starts with no charge, bromine starts with a -1 as a bromide ion, and then they swap over. So there must be transfer of electrons happening from one element to another in all of those. So I'm just using the fact that there's an element on any side of the equation is a quick way to spot that you've got a redox reaction happening. There is one last definition which is going to be far more important at A level, which is that oxidation is an increase in oxidation number and that reduction is a decrease. But don't worry if you haven't covered this yet, you'll do it in a lot more detail in the redox topic.